Right, you thought we were done with systems. We're not quite done with systems, but this time we're doing inequalities rather than equations like we've been doing in the past couple of sections. So some of the things we're going to do, we're going to review solving inequalities, which you've done before. We're going to write inequalities, describe those in real life situations, graph those systems of inequalities, and interpret those inequalities. We're going to talk about something called a feasible region, and we're going to find the vertices of a feasible region. So first of all, let's just do a little bit of review. We have just slope-intercept form, right? So just review slope-intercept form. It's easy to graph a line when we're in slope-intercept form. We can see from what we have here in our equation that our y-intercept is -1, and we have a slope of 2/3, or rise of 2 and run of 3. So 1, 2, up 2, and over 1, 2, 3, right? So 2 points makes a line. Find our 2 points and graph that line. So that's just a quick review. Just be careful about which number is the slope and which number is the y-intercept, because sometimes our equations are going to be in intercept form rather than slope-intercept form. So know that the slope always belongs with the x, right? So our slope here is -2/1, and our y-intercept is 3. So we're going to start at 3. Remember, y-intercept is a starting point, and our rise is going to be -2, and our run is going to be 1. So I'm going to go down 2 and over 1, and there we can connect those dots to make our line. Right? Remember, though, a line does not have to be in slope-intercept form in order for us to be able to graph it by hand. Standard form is also easy to graph if we can find our x and y-intercept. So I'm going to do a quick review of that as well. So this is in standard form. Now remember, when I say standard form, I mean ax plus by equals c. Right? There's our standard form. I don't see an intercept. I don't see a slope right now. But we could find our x-intercept and our y-intercept by simply substituting 0 for each of those variables. So in other words, if I want to know where that line crosses the y-axis, x is going to be 0, right? So 2 times 0 minus 3y equals 12. Well, essentially that then cancels out. That's a 0, right? So I'm going to divide by -3. And I get y equals -4. So my y-intercept is -4. I'm going to turn around and do the same thing for my x-intercept. So if I want to know my x-intercept, I'm going to replace y with 0. So again, essentially, I'm getting rid of my y term, and all I have left is my x term. So if I divide by 2, I get x equals 6. So my x-intercept is 6. So again, I have 2 points. I'm going to draw a really not very straight line, I don't think. Oh, not too bad this time around. 2 points make a line, and there's my line. And so you're going to remember that standard form. So just one more quick example. I replace x with 0, getting rid of that. And my y-intercept is 8/3, or 2 2/3. That's my y-intercept. And again, whoops, that was fun. Let's try that one more time. If I replace y with 0, I'm essentially getting rid of that term. I'm going to divide by 4, and I get x equals 2. So my x-intercept is 2. I have 2 points that make a line. Right? You're, of course, going to use a straight edge to graph your lines. Let's take a look at this one. So this is an inequality rather than an equation. So notice that I have an inequality symbol. This is a relation symbol that's not equals. And that involves shading on one side or the other. So I'm going to graph this exactly the same way as I was graphing it before, but this time I'm going to shade. So I see a y-intercept of -2 and a slope of 3/4, right? So 1, 2, 3, 1, 2, 3, 4. Right, so that's already graphed for us, but this is greater than or equal to, right? So where do you think I would shade, above or below this line, if my symbol says that y is going to be greater than the line that I have on that graph? Well, if I'm looking for things that are greater than, then I'm going to be shading above that line. So this inequality involves graphing my line and then deciding where I'm going to shade, above or below. Now also notice that this is a solid black line, right? That solid line is because it says equal to. So that solid line is going to be also equal to. It's going to have that one line below, greater than, I'm shading above. So let's look at another example. So 2x minus 3y is greater than or equal to 6. Well, again, to graph my line in standard form, I get rid of my x term. I have negative 3y is greater than or equal to 6, divide by negative 3, and I'm going to have my y-intercept, right? So my y-intercept is negative 2, so I'm going to mark that y-intercept. Now I'm going to go back and I'm going to find my x-intercept by substituting a 0 and essentially getting rid of that term. This time I'm going to divide by 2 then, and I'm going to get x equals 3. So I have my line, graphing that in standard form. Okay. Now, you have to be careful about this one. There's some things you have to remember when you solve an inequality. So I'm going to go back here, and I'm going to get this in slope-intercept form here real quick, just to make sure that we're graphing it in the right, or just to make sure we're shading the right region. So you notice this says greater than or equal to. So right away I think, oh, I'm going to shade above. Well, let's just double check that and make sure. If I were to solve this for y, I'm going to subtract 2x from both sides, and I'm going to get negative 3y is greater than or equal to 6 minus 2x. Okay. Now to finish this off, I'm going to divide by negative 3. This is where you have to be careful. So now I have y, right? Recall back from solving inequalities. When I divide or multiply by a negative value, so because I'm dividing by a negative 3, I have to make sure that I flip that symbol around. To show that I'm changing signs, I need to flip that relation symbol. So now what do I have? 6 divided by negative 3 is negative 2. And then I have negative divided by negative, so positive 2/3 x. So now if we look at our final equation, or sorry, final inequality right here, what region am I actually shading? Well, this now says less than or equal to. So I'm actually, for this one, I'm going to shade below that line, right? So you have to be careful when it's in standard form. You can graph that just fine by finding your x and y values, but you have to make sure that you're actually shading the right region. Okay, let's just check a point real quick. This is another really great thing to do to check yourself when you're graphing inequalities. So I shaded below, right? I'm going to go back up to my inequality, and I'm going to pick a point where I shaded, because what that shading is saying is that anything in that region is a solution to this inequality. So let's just pick an easy point, 3, negative 3. Okay, I'm going to substitute that back in. So x is 3, and y is negative 3. And I'm going to make sure that that ends up being a true statement. So here I have 6. I have negative 3 times 3, so plus 9 is greater than or equal to 6. Is that true? Well, yeah, 15 is greater than or equal to 6. So it looks like that point works. That point is in my shading, so it looks like I have shaded in the right place. Now if I go back and I pick a point where we didn't shade, so everything up here is not a solution. So everything in the shading, those are solutions to that inequality. Everything above that, where it's not shaded, is not a solution to that inequality. And so if I pick a point up there, and I'm not going to do this, you can do this if you want. If I pick a point up in this region where it's not shaded, say 0, 1, and I substitute that in here, that shouldn't work for that inequality because those are not solutions. Okay? So how are these two graphs different? Let's take a look real quick. So this is now, remember a little bit ago I mentioned that solid versus, or just mentioned a solid line. So we're going to take a look at when I don't have a solid line for an inequality. So this is y is greater than 2x minus 1. All right, so slope-intercept form, so that's nice. I have a negative 1 for my y-intercept, and I have a slope of 2. So up 2 over 1, right? All right. And then I'm going to go over to this one, and same thing, y-intercept of negative 1, and a slope of 2 over 1. So 1, 2, and over 1. Right? So same slopes, same y-intercept. The only difference you'll notice is this. Right? So I have y is greater than 2x minus 1. What that tells us for this one is that because it's not equal to, that line is going to be dashed. So if it does not include the equal to sign, that is a dashed line. Still going to shade above, but that's telling me that the points on that line are not solutions. Only the points above. Nothing on the line is a solution. Okay, so in other words, if I pick something on the line, negative 1, negative 2, that's not going to work in that inequality because it's on the line. Now this one is greater than or equal to. So in this case, I'm going to have a solid line because everything on the line actually works this time because it says y is greater than or equal to. So that line also represents solutions to this inequality. Okay, let's just do a quick check. So if I pick something on the line, negative 1, negative 2, that should work. Y is greater than or equal to, oops, I got a substitute there, right? So I have negative 1, negative 2. So negative 2 is greater than or equal to 2 times negative 1 minus 1. Well, is that true? Negative 2 is greater than or equal to negative 2 minus 1. Negative 2 minus 1 is going to be negative 3. That is a true statement, right? Let's see. You know what? I think I picked a really poor point on that because my line is not straight. So sorry about that. Let's ignore that last step. If I were to pick an actual point on that line, I'd actually get something if I drew this nice and straight, right? My point would actually be down here. So let's try that one instead. Negative 1, negative 3. So negative 3 is greater than or equal to 2 times negative 1 minus 1. Negative 3 is greater than or equal to negative 3. So it's negative 3 is not greater than negative 3, but negative 3 certainly is equal to negative 3. So that is a true statement. Everything on that line works as a solution. On this line, that does not work as a solution, so that has to be a dashed line. So if I chose that same point, I would get negative 3 is greater than negative 3. Absolutely not. That doesn't work. So nothing on the line is a solution. It's got to be dashed. All right. The system of linear inequalities is having two or more inequalities and finding where their graphs overlap. All right, I'm going to split this up into two sections here. So one, we're just going to do one of these examples, and then I think we're going to finish this off in another section just to make sure this doesn't get too long here. So just a couple things to notice about this. My first inequality, I have greater than, right? Not greater than or equal to, greater than. So right away, I know that that's this line because it's a dashed line. There's not an equal to, it's a dashed line. So above that line, greater than, I'm going to shade right here, right? Okay, this is going to look a little messy, so just bear with me. Shade a little bit more over here, right? Okay, so everything above that line is shaded. My other one, less than or equal to, so again, notice that that's a solid line because of that equal to, solid. and it's less than, so I'm going to shade below the other line. All right, so below this solid line is going to be right here. All right, that would be considered below. So notice where the green and blue overlap. So everything in this area here, okay, and of course if we continue that coordinate plane, that would continue off to the left. It doesn't just, stay in this one region. But everything in that plane, to the left, the lower left of the solid line and up above that dashed line, those are all going to be solutions. So if I pick something in here where the overlap is, I'm going to find a solution to that system. And I know this is really messy. Here's what I'm going to do. I'm going to make our solution area. I'm going to clear that off. So now our solution area is clear. So everything in this overlap was a solution. That's not supposed to be overlapped. Okay. So this was our overlap. Let's pick a point in that overlap. This is a really good way to check, to make sure that, you have a region that actually includes the solutions. So my point is negative 3, 1. All right, so I'm going to go ahead and substitute that into my top inequality. I keep wanting to say equation. Into my top inequality to see if that works. So y is 1. It's greater than, so this is what I'm doing right now, greater than 1/3 times negative 3 minus 2. So 1 is greater than, well, 1/3 of negative 3 is negative 1 minus 2. 1 is greater than negative 3. Check. Works for that one, right? All right, so we're good for the first one. Let's try the second one. So same point for both. So I have 1, now this time is less than or equal to negative 2 times negative 3 plus 3. So 1 is less than or equal to 6 plus 3. 1 is less than or equal to 9. Again, check, that is a true statement. So the point we chose that was in our overlap did work for both of those. So it looks like the region that we overlapped was a good region. That's called our feasible region. I'll bring that word up again in the future, but for now I think we're going to stop there.